Hello. In this video, I would want to introduce one final method that can be used to calculate the expectation of a random variable. By the end of this video, I would hope you would be able to state the condition expectation theorem, which is the idea that we're going to use to calculate these random variables, and that you would be able to calculate the expectation and variance of the geometric random variable using the condition expectation theorem. Before I get onto that though, I want to remind you of an idea that we studied in a previous video, the partition theorem. If you remember, in that video we drew a Venn diagram, something like this one here, in order to show that you could calculate the probability that the random variable capital Y takes on a particular value, small y, by adding together the probabilities that capital Y equals small y and that capital X is equal to the full range of its possible values. We wrote the final expression that we arrived at in terms of conditional probabilities as shown here. If you've forgotten this material, please go back and re-watch this video on the partition theorem now, as understanding this idea is critical to understanding the condition expectation theorem that we will discuss here. Given that you've carried on, I will assume that you are now completely comfortable with the partition theorem and the way that it can be used to calculate absolute probabilities. Here, this rule is again stated at the top of this slide. In addition, I hope that by now you are also comfortable with expectation values and are happy enough for me to write the expectation value of the discrete random variable capital Y as shown here. I can combine the two ideas in these two equations by noting that in the right-hand side of my expectation formula, I have the probability that the random variable capital Y is equal to Yj. I can calculate this absolute probability using the partition theorem above, and I can thus rewrite my expectation value as follows. Next, I can reverse the order of the summation signs as shown here and arrive at this result. If you look at the circled part of this equation, this looks a bit like an expectation value. You have a sum over all the possible values the random variable capital Y can take, and inside this summation you have the various values that the random variable capital Y takes multiplied by the probability that the random variable is equal to Yj. Notice here though that this is no longer the absolute probability that capital Y equals Yj, but is instead a conditional probability that the random variable Y equals Yj, given that the random variable X equals Xi. This circled summation is thus said to be a conditional expectation value. It is the expected value of Y given that the random variable capital X is equal to Xi, which we can write using the following shorthand. The result we have arrived at is known as the condition expectation theorem. It is shown again on this slide in the form that we just wrote it above. I like to write it this way as I think it is easier to understand. In many notes and textbooks, however, you will see it written as shown in the manner shown in the lower equation though. Writing it this way recognizes that the quantity in the top equation is just an expectation of a function. The function in question here being the conditional expectation value of Y given X is equal to Xi. If you look at the top equation, we have a sum over all the possible values that the random variable capital X can take. Inside this summation, you then have a function of Xi, the conditional of expectation, multiplied by the probability that the random variable capital X is equal to Xi. This is just the formula for the expectation of a function of a discrete random variable. This is all well and good, but what is the point? Well, to see the point, let's consider the following problem. A family decide to have children until they have their first baby girl. Calculate the expected number of children in their family. You may assume that the probability of having a girl is p, and that the gender of the first child and any subsequent children are independently distributed random variables. Now the family size here could be any number between 1 and infinity. infinity. Admittedly, it is unlikely that they will have 15 baby boys before finally having a baby girl, but when calculating the expectation, we need to consider all these possibilities. The range of family sizes that we must consider when calculating this expectation thus goes all the way from 1 to infinity, and the summation that we must perform if we want to solve this problem directly looks a bit tricky. We therefore choose to use the condition expectation theorem instead. We introduce two random variables, capital X, the gender of the couple's first child, and capital Y, the number of children in their eventual family. We thus write the condition expectation for the expectation of Y, the size of this family, as follows. When we do so, we say we condition on the gender of the first child. There are two terms in this expression, as the first child can be either male or female. Arbitrarily, we decide that if the baby is male, the random variable capital X is equal to 0. When we consider the first term in this expression, we are thus considering what happens when the first child in their family is male. The second term, in which capital X equals 1, thus concerns what happens if the first child is female. We are told the probability of having a female child in the question is equal to p, and so we can substitute p for x equals 1 and 1 minus p for x equals 0. In addition, the question tells us that the family will stop having children once they have a little girl. Consequently, if their first child is female, they will only ever have one child, as in this particular couple's mind, they need no further children in their perfect little family. The conditional expectation, the expectation of y, given that capital X equals 1, is thus equal to 1. As every time their first child is a girl, they will have no further children. The size of their family, capital Y, will thus be 1 every time this happens. We are thus left with one final term in this expression to determine, the expectation of capital Y given that x equals 0. It turns out that this expectation is also rather straightforward to calculate, in large part because the gender of the first child has no effect on the gender of the second, which implies that the number of children in their family will be equal to 1 plus capital Y. Now it is important to stress that capital Y here is a random variable. The size of their family is still random. However, because the gender of their first child does not affect what happens when the woman of the couple gets pregnant once more, the cumulative probability distribution function underlying this discrete random variable is identical to the cumulative probability distribution function of the random variable y for which we are trying to calculate the expectation. This is a profound point and one that demonstrates the huge advantages of the random variable notation that we have been using throughout these videos. If you are a bit confused, it might be worth pausing the video for a moment to think about what this means for a little while, as this sort of thinking is really one of the key ideas in the course. Okay, so hopefully you've had sufficient time to reflect on the fact that the size of the couple's family, if their first child is male, will be equal to 1 plus y, where y is a random variable. We want to calculate the conditional expectation, the expectation of the random variable 1 plus y, which is easy to do because we can exploit the fact that the expectation is a linear operator. We can thus write that the expectation of y plus 1 is equal to the expectation of y plus 1, as shown here. Substituting everything into our equation and multiplying out all the brackets, we thus finally arrive at the equation shown here. In this expression, we can cancel out the factors of plus p and minus p, and also the factor of the expectation of y on the left and right hand side of the equation. We thus arrive at a rather simple expression that we can rearrange to get and find that the expectation of y is equal to 1 over p. Now that was rather straightforward. What is more, you realise just how straightforward this was when you try and calculate the expectation of this random variable via the moment generating function, root, which is a gigantic pain in the arse, trust me. Nevertheless, let's try a second problem just to make sure we have understood the relevant steps in this procedure. This time, we would like to calculate the variance of the family size y. As you by now hopefully know, to calculate the variance we need to calculate the expectation of y squared. We can do this by conditioning on the gender of the first child, the random variable capital X, just as we did in the previous example. The final formula we arrive at when we do so is shown here. Within this formula, we can exploit the same logic we used in calculating the expectation of y to determine the probability that x equals 0, the probability that x equals 1, and the expectation of y squared given that x equals 1. For the last of these, remember that if the family's first child is female, they will only ever have one child, and thus the size of their family, capital Y, will be equal to 1 with certainty. As such, y squared will also be equal to 1. And the conditional expectation of y squared, given that x equals 1, will be equal to 1. The value of the conditional expectation, e of y, the expectation of y squared, given that x equals 0, is once again the most difficult term to determine. Once again, though, we can use the logic that we used in calculating the expectation of y. We know that the gender of the second and all subsequent children will not be affected by the gender of the first child. Hence, if their first child is male, the size of their family will be y plus 1, where y is a random number. The conditional expectation, the expectation of y squared, given that x equals 0, is thus equal to the expectation of y plus 1 all squared. Here again, it is perhaps worth pausing for a moment to have a think and take that in. If you have understood why the conditional expectation of y squared given x is equal to 0 is equal to the expectation of y plus 1 all squared, the rest of this problem is child's play. You simply multiply about the brackets inside the expectation operator as shown here. You then exploit the linearity of the expectation operator and rewrite the expectation of y squared as the expectation of y squared plus 2 times the expectation of y plus 1. Substituting all this into the top equation and replacing all instances of the expectation of y with the value 1 over p that we determined on the previous slide, we can then rearrange, cancel terms, and arrive at the following expression. When this result and the result from the previous slide are substituted into the definition of the variance, we thus get to the variance of y is equal to 1 minus p over p squared. To summarise then, we have learnt the condition expectation theorem as shown here. In our example with the family, we have then used this theorem to determine the expectation and variance of a geometric random variable. As always, I hope you have understood this video. If you haven't though, try watching it again and see if it's any clearer on the second time through. Thank you.